Alright, what is going on? So I'm going to try to go over this problem, Leetcode problem 1488, avoid flood in the city. So this problem turns out to be kind of like a hash table problem. Really using the hash tables to kind of keep track of some things. That's really how you kind of solve it. So like what I did was, the essential idea behind it is it's kind of like a sliding window in a sense, maybe, but what I have to do is, for a problem like this, right, what you have to do is basically keep track of the day when it last rained. So the couple of things I keep track of is the last, oh my gosh, last rain. So we kind of keep a table for this, whatever, something like this. And then also keep a table for the lakes, basically if it's rain there or not. By keeping track of these, the last rain will give you the index. By using the index, you can always say, if so I go through this array, right? So I get the one. The one, I'm going to add to my lakes, and what I'm going to do is I'm going to say, give it a 1 value. 1 signifies that it's full of water. And then we go to this 2 here, or the 0, and at the 0, we look and we say, this is a dry day, so we keep track of our dry days that we can use. Really, we keep track of the index, so the index is 1, so we have that. We go to this 2, we add the 2 to our lakes. 1. And we also add the index when it rained there. So it rained here at the 0, it rained the 2 at the 2 index. Now this is crucial. This hash table is crucial to solving this problem. I will tell you that, because, yeah. So then what we do is you append it looks like we have 0, 1, 2, 3, so we get 3 as another dry day. Then we go to this 2 here, and this 2, we see it's in my lakes, so we're like, okay, it's rained here before, so in order for me to be able to accept this, for it to not overflow, there must be a dry day available that I can use. So we look at the last rain based off of this lake, and we see the index is 2, right? So we take that 2, we search through dry to find an index value greater than 2, which is this 3. So we're like, hey, we can use the 3rd day to dry out lake 2. And then that's good. And then for this 1, for the 1, we look at the index is 0, and this 1 here, like we pop this out of our dry, and we say 1, okay, well, we could use this day to dry out 1. So that works really well for this case, but consider if you have Okay, so let's see, what if we have this example? So we can kind of see that our last rain is going to be like 1 will be at 0, 2 is going to be at 2, it looks like, and then we're going to have some dry days. We're going to have dry day at index 1, at index 3, and 4, and then this is last rain, and then lakes. Our lakes are going to be, we're going to say 1 and 1 and 2 and 1. So we say, hey, we've seen these lakes. So then what happens is this. Right, so we see this 1 here. And this 1, so my thing's kind of greedy. It says this 1, it wants to find the best option for this 1. So it looks based off of when it last rained at 1 was at index 0. So let's use this one. So we pop out this and we use this to dry 1. Okay, so we're good. We haven't flooded. And then I'm going to update the last rain for the index to be 0, 1, 2, 3, 4, 5. So it's 5 now. you can't see that, but I update the index for this 1 to be 5. So then we go to this 2 here. Oops, this 2 here. And this 2, we're like, oh, hey, we've seen 2 before. Let's see if we can dry out the previous one so that we're good. So we see index 2, right? So we go and we see, well, this index 3 is greater than 2, so we use that. We update this index to be where we're currently at, which is 6. Then we go to this next 2 and we say, okay, hey, we've seen this before, right? So basically the 1 means that you've seen it before. So we're like, hey, we've seen this before, so we need to make sure that we can make sure that it doesn't overflow, right? So we're going to make sure that we can dry this 2 here. But then we look, our index is 6 now, right? There's no dry days after 6. There's no dry days between here. So that's what you're doing here. You're keeping a list of the indexes for the dry days, and then you're keeping track of when it last rained there, because you need to find between when it last rained there and when it's currently raining there. Then you need to see if there's a dry day available. If there's no dry day available between those 2 days, it doesn't work. So you're trying to find a patch, where there's basically no dry days between them. And that's why you keep track of when it last rained there, and you keep track of the index for the dry days. Another interesting aspect is, so when I'm using this lakes list over here, this lakes list is really just something to like tell me that if I've seen it before. So it's like, oh, we've seen 1 before, right? So we're like, okay, so we have to check when it last rained there. So basically, if we've never seen a lake, it has never rained there, so we don't have to check if it last rained there. So I just realized for lakes, all you need is a set. So I'm going to actually improve this. So all you need is a set for this. I don't know why I have this. Oops. Yes. Okay. And then what you do is you do this. So this is what the code looks like. So I'll go over the code. So n equals length of rains. Oh, why did I do this? Okay, I never actually ended up using this line. Okay, so here we have res. So result are lakes. So it's going to be a set, a hash table, and our last rain, a default dictionary or a hash map, and then the dry days. So we enumerate through the rains. So I will be the index. It starts at 0, so assign 0, and then the lake will be the lake number. It might be 0, right? So if the lake is equal to 0, then that means that we just want to append that to the dry, and we want to append 1 to the res, because what I'm doing in my code is I just set, like, sometimes a dry day might not be used to dry out a lake. In that case, I just by default set it to 1, so it's like my default setting. So I continue, you don't go down here. Otherwise, go down here, put res append -1 because you're hitting, it's raining. And we check the lake, we check if it's greater than 0, but now I don't need to do this. Instead, I just need to check if it's in lakes. That's all I need to do. Because if it's in lakes, I need to make sure that there's a dry day between the 2 when it last rained there. So first I check, okay, well, if this is the case, if lakes are in lakes, we kind of need to check that there's a dry list. If there's no dry list, just return nothing. We get the index for when it last rained there. We update the last rain to be where we're currently at, right, this current I, so our current index. We update to say, hey, now, because we're raining right now, right? It's raining right now, but we're seeing if we can dry it up before it rains right now. But this rain right now could have bad effects for later. And then found is false, and then I do a for loop through here, and if d is greater than the index, where index is basically the index when it last rained, if we can find a dry day, then we just, we add that, we use that for our result. We use that lake, we say, hey, we dry this lake on this day, we pop it out, and we set found equals true. If not found, we return that, which is what would happen in the case when you have like these 2's together, because it would like look between, it wouldn't find any dry days available, so it would do this. And then else, this is if, I guess, if we've else we would do this, or if we haven't seen the lake before. I don't know why I did it. So all you want to do is add to lake. You want to add lake. That's all you want to do, and then you update last rain. Okay, run this code, and then I'll submit it. Okay, so cool, it worked. It's an interesting problem. So it seemed like this problem is most related to basically using hash tables and hash maps to be able to solve it. And like the key for me, the most important thing was just keeping the index of when it last rained there, and then making sure you find a dried index, a day that you can dry on, that's greater than that index. And this is kind of like a greedy algorithm. But that was the most important part for me, like figuring out that. The rest just works out. And then also, it's kind of a greedy algorithm. It's just optimal. It's not really looking ahead or anything. The time complexity is about O of n squared, because we're enumerating through the range. So we're gonna the length of the range, and then we also enumerate through dry. So if there's a lot of dry days, this could be running at O of n squared. Plus we got this pop j here, which is going to add on something else. So I think it's about O of n squared.